Now let's look at Appendix A, Statistical Reasoning in Everyday Life. Statistics are important tools in psychological research, but statistics also benefit us all by helping us see what the unaided eye might miss. To be an educated person today is to be able to apply simple statistical principles to everyday reasoning. In this appendix, we look at how to describe data using measures of central tendency and variation and so on, and at significant differences, asking how to determine when an observed difference is reliable and significant. First, let's look at examples of where sometimes statistics can be somewhat misleading to us. An American truck manufacturer offered a graph, listed in graph A here, with actual brand names included to suggest the much greater durability of its trucks. What does graph B make clear about the varying durability and how it is accomplished? So look at those two graphs. Well, obviously they're different. Okay, you can see in graph A that our brand seems significantly better than brand X, brand Y, or brand Z. However, if we look at graph B, we see that all of them seem basically equivalent to each other, the same. The grand scheme of things, what we're saying here is misleading at best and lying at worst by the brand owners here. So our brand is trying to pull a fast one in a way. So look at more carefully. Note how the y-axis on each graph is labeled. The range for the y-axis label in graph A is only from 95 to 100. The range in graph B is from 0 to 100. All the trucks rank as 95% and up. So they're all really quite well when it comes to durability. There's really no real difference after 10 years of functioning. And that's what graph B makes clear. However, in the original graph, graph A, they're trying to mislead you a little bit by making these differences of 5 percentage points much greater than they actually are. So yes, they may be a little bit better, okay, but not a great deal, or nor is it significantly better than the other brands X, Y, or Z. Now, let's look a little bit at distribution. We can look at distributions by measures of central tendency. What we have here is a skewed distribution. This graphic representation of the distribution of a village's income illustrates three measures of central tendency: the mode, the median, and the mean. Note at the far right of this graph, note how just a few high incomes make the mean the fulcrum point that balances the incomes above and below deceptively high. So let's imagine that we're talking about $140,000 or something of that nature for a particular village. That is seen as the average. But that average is being inflated because of some extreme scores. We have 950, 1420 at the very far right. These are heavily weighted, okay, and they change and influence the average, the mean. So let's look really closely here. The simplest measure is the mode. That is simply the most frequently occurring score or scores. In this case, we can see the mode is 40. The most familiar to us is the mean, or the average, the total sum of all scores divided by the number of scores. And in this instance, we say 140. But again, we've already noted that this is somewhat deceptively high because of these scores here at the extreme end. The midpoint, the 50th percentile, is the median, just the midpoint. On a divided highway, the median is in the middle, and that's what we see here. So the midpoint is here, 60. Mode 40, median 60, mean 140. So the range of scores is the gap between the lowest and highest. It provides only a crude estimate of variation. In an otherwise similar group, a couple of extreme scores, such as 950,000 and 1.42 million income, as in figure A2, will create a deceptively large range. The more useful standard for measuring how much scores deviate from one another is the standard deviation. It better gauges whether scores are packed together or dispersed because it uses information from each score. Now let's look at this normal distribution here. Figure A3 shows a useful property of the normal curve is that roughly 68% of the cases fall within one standard deviation on either side of the mean. So you can see in the middle of this bell curve here, we have 68%. So 68% of the scores tend to fall here in a normal distribution. So 68% of the cases fall within one standard deviation of either side of the mean. About 95% of the cases fall within two standard deviations here. We see this outlined with the blue, shaded light blue here. 13.5, 13.5 here. All right. Thus, as Chapter 9 notes, about 68% of the people taking an intelligence test will score within plus or minus 15 points of 100. About 95% will score within plus or minus 30 points. So with a lot of factors, a lot of phenomena, they fall within a bell curve, a normal distribution. We can have expectations that scores will fall mostly here, with smaller amounts of scores falling in the tail ends of the bell curve. And when you hear about someone curving grades, they're talking about the normal curve here. They're making the scores of a test, for example, fit this distribution of scores more closely. So here, let's look at this again based on the measures of central tendency, which we've already gone over. The average of a distribution of scores is the blank. What is it? The score that shows up most often is the blank. The score right in the middle of a distribution, half of the scores above, half below, is the blank. We determine how much scores vary around the average in a way that includes information about the blank of scores by using the blank blank formula. So basically, it's this. The average of distribution of scores is the mean. The score that shows up the most often is the mode. The score right in the middle of the distribution, half above and half below, is the median. We determine how much scores vary around the average in a way that includes information about the range of scores by using the standard deviation formula. Now, let's look a little bit also at something we talked about in the previous session, correlation. As we saw in Chapter 1, describing behavior is a first step toward predicting it. So descriptive stats, that's what it does. It just simply describes what's going on. Then the notion is we want to look at correlation. So when naturalistic observation and surveys reveal the one trait or behavior accompanies another, we say that the two correlate. A correlation coefficient is a statistical measure of the relationship. In such cases, we use scatter plots that can be very, very revealing. So the perfect positive correlation is a correlation of 1. That's on the far left here. The middle, no relationship again, correlation coefficient of 0. And then here, a perfect negative correlation, again 1. Think about this. If I had several correlation coefficients, and one was 0.5, and one was negative 0.7, which is a more powerful relationship, the 0.5 or the negative 0.7? The answer is the negative 0.7. The negative simply tells us the type of relationship. The 0.7 tells us the strength of that relationship. So a positive 0.5 is still going to be a smaller relationship compared to a negative 0.7. The negative just tells us the type of relationship. As one variable goes up, the other variable goes down. A positive just tells us, again, the type of relationship. As one variable goes up, the other variable goes up. Correlations, abbreviated R, can range from +1, scores from one variable increase in direction proportion to scores for another, to 0, no relationship, to -1. Scores for one variable decrease precisely as scores rise for the other. Comparing the columns in table A1 here, most people detect very little relationship between height and anxiety. In fact, the correlation in this imaginary example is 0.63. What you would do is you see each one, 80, score 80 inches, 75, 63 inches, 66 anxiety scores. We can correlate them together to see how closely they relate to one another. It's basically the same type of thing that you see for when you are applying for college. They are very interested in your high school GPA. All right, the high school GPA is usually going to be correlated with a certain semester term of your first year in college. So when they get that number of your high school GPA, they can use that to help figure out what your performance would be like during your first semester at a college. So looking at the scatter plot for height anxiety, this display of data from 20 imagined people, each represented by the data point, reveals an upward slope, indicating a positive correlation. The considerable scatter of the data indicates the correlation is much lower than a positive one. So we can see that there is a theme that it seems to be going in a positive direction, but it's rather fat. It's like a blob, like a saucer. Okay, if it was more like a fat cigar, we would think it would be a stronger correlation. If it was a straight line, obviously, and all the data points fell on that straight line, again, it would be a perfect correlation. So the scatter plots give us a real good idea of the type of correlation that we're looking at.